Hello, we are Sonia, Menelaos, and Richi from Team 1059. We are presenting our solutions to problem A about micrometeorites and their journey. Our presentation consists of the following sections. So the first one is introduction. Our cosmic dust is made of tiny solid particles drifting through space. Some survive their journey through the atmosphere and land as micrometeorites, while others are destroyed by ablation. This means that they vaporize as friction and wind drag slows them down. As we study these grains, we will often refer to their flux, which is the number of particles passing through a given atmosphere each second or year. We made several assumptions about the cosmic dust to help with our models. First of all cosmic dust pass generally, which means that they are not affected by violent contacts in space. The source of particles are also homogeneous, and a group of particles would have the same angle of entry. This means that they fly in parallel and there is no collision between each other. We also assume linear drag with small corrections, and the wind drag is the opposite directions to the falling angle of the particles. Onto the particles themselves, we assume that they are spheroids in shape, which is consistent with many research. We will be considering different sizes in our calculations, but they can be between 10 to 5,000 micrometers in diameters.
So the goals for our project are threefolded. First, we will create a model to estimate cosmic dust distribution found within a given strata of the Earth's surface from a certain time period. Afterwards, we'll work backwards to estimate the distribution of particles that enter the Earth's atmosphere. Lastly, we will provide an initial estimate what happens to the particles as they enter the Earth's atmosphere by calculating ablation, velocity, varying angles, and testing other different parameters. So at first, we will estimate the distribution of particles of cosmic dust found within a given strata of the Earth's surface from a certain time period. We assume particle ready follow a non-normal probability distribution. Each particle's mass is computed assuming spherical geometry. The total mass of cosmic dust deposited per unit area over a time interval depends on the incoming flux F in and the preservation fraction eta, which accounts for the fraction of particles that survive atmospheric entry and environmental loss processes. The unnormalized mass fraction combines the particle mass and the size distribution. Normalizing this quantity will give us the proportion of total dust mass contained in each size bin. Finally, dividing the mass in a bin by the mass of an individual particle yields NR, the number of particles per unit area for radius R. This slide shows the different parameters we used for our formulas in the previous slide. These are some of the parameters we used in our model based on literature, and we kept them constant throughout our model. These are the results for our part 1. We varied the median radius of the log normal distribution to see how it affects the number of particles deposited. A smaller median radius produces far more particles because the distribution shifts towards smaller sizes where many more grains are needed to account for this mass. Larger median radii concentrate more mass in fewer, bigger particles, resulting in a lower particle count. We also varied the incoming cosmic dust flux to examine its impact on the number distribution. As expected, a higher flux produces more particles across all size ranges. Conversely, a lower flux reduces the number of particles in every size bin. We varied the deposition interval delta T to examine how the number of particles in the sediment changes over time. A longer accumulation period naturally results in more particles being preserved per unit area, since dust continues to settle and build up over a greater number of years. Finally, we changed the preservation fraction to show more preservation fraction results in greater accumulation. This demonstrates that particle abundance is directly influenced by how much material is preserved over time.
So with the supposed distribution on a given area of the Earth's surface, we can now model to estimate their distribution on entry. We do this by reversing the formula for number of particles in each size bin and adapt other formulae to produce the estimated flux that must have entered the atmosphere. We use parameters from observation of the surface distribution, as well as parameters that we theoretically assumed about the atmosphere and particles. We also tested behaviors of the models with varying parameters, where we applied an example function of number of particles on the Earth's surface. So here are some of our graphs of different parameters varied. As we can see from most graphs, particles with higher radius have lower distribution in the atmosphere, and there is a large number of small particles. This makes sense when comparing to the model of distribution on Earth, as the majority of small particles would suffer from ablation and not reach the Earth's surface.
And so here we present the third and final part, that of simulating the atmospheric entry of cosmic dust particles to determine the survival and final distribution on the Earth. And so we proceed the mathematical and physical model. And so here we present a mathematical model describing a particle's entry into the Earth's atmosphere. And it is a set of three coupled equations for velocity, mass, and altitude, capturing the drag, gravity, and ablation, as you can see on the top left. Because these equations are non-linear and interdependent, we solve them numerically using the Ronca-Kara fourth order method with small time steps to track the particle's descent accurately. This slide shows the physical model used in our simulations. We modeled the atmosphere with an exponential density law fitted to the US standard atmosphere data, giving the R0 and scale 8 values as shown in the figure, with constants defined on the right. And so for the results of the part 3, in the first experiment, we varied the particle size while keeping the speed, angle, and composition fixed, and small grains under 200 micrometers fully ablated, while larger ones survived to the ground. The survivors retained about 5% of their mass, as you can see, revealing a critical radius around 100 to 200 micrometers, the threshold between atmospheric dust and micrometeorites. In the next part, the first graph shows the larger particles keep their higher final speeds. On the right, we see the entry paths of those that reach the ground, forming a clear survivor corridor. Smaller grains decelerate early, while larger ones stay fast and fall almost ballistically. Keeping the radius fixed at 250 micrometers, we varied only the entry speed. Higher speeds cause stronger heating and ablation, so particles stop higher or lose most of their mass. Above about 14 kilometers per second, a 250 micrometer grain cannot reach the surface. It remains as high altitude dust. And so this slide shows that as the initial speed increases, ablation becomes much more intense, which in turn results in a significantly reduced final speed. Here, we vary the entry angle while keeping the radius and speed fixed. The angle is measured from the horizontal, so 90 degrees means a vertical descent, and shallow angles create long paths through the upper atmosphere, increasing drag and ablation. Particles slow and burn up higher, while steeper angles are shorter and more direct, allowing grains to retain mass and reach the ground faster. So from the graph in the next slide, higher entry angles from the survival angle particles means higher final speed when reaching the ground. And so in the fourth and last experiment of part 3, we tested how composition affects survival. Light carbonaceous grains burn up, while dense metallic ones penetrate deeper and reach the ground.
So these are the limitations for our model. So in our model, we made several simplifying assumptions. We assumed a log normal size distribution and treated all particles as spherical. We also used a single preservation fraction, even though survival likely varies with size and composition. Our model doesn't include atmospheric filtering, chemical alteration, or post-depositional loss. We relied on a theoretical size distribution for particles entering the atmosphere and for those recovered on the surface. And we assumed a common travel angle for all micrometeorites. Finally, our estimate of atmospheric particle distribution depends on an assumed ablation rate parameter. These limitations show where future refinements could improve accuracy. So these are the conclusions from parts 1, 2, and 3. So from parts 1 and 2, we can summarize that particle sizes on Earth follow a non-normal particle distribution. Smaller grains are far more abundant. Longer accumulation and preservation increase how many particles survive in sediments. And higher preservation lowers the invert flux, while smaller median sizes and longer deposition times shift the reconstructed flux towards smaller and more numerous particles.
For the conclusions for part 3, we examined how size, speed, angle, and composition determine micrometeorite survival. So grains smaller than 200 micrometers or faster than 14 kilometers per second burn up, while larger, slower ones survive. Steeper angles and dense metallic materials favor survival, with shallow or fragile grains vaporizing. Next, we'll include heat transfer and fragmentation to better match real micrometeorite data. These are our image credits and references. And finally, thank you so much for your attention.